Hi, good. Am I audible? Okay. Hi, good afternoon. I am Umang, and I'm going to be talking about heap manipulating programs and the verification and a decidability result that we have in this context. And this is joint work with Aditya, Paul, who are in the audience, and Madhu and Mahesh, who are professors at Illinois. So let me talk about the problem statement that we are talking about. We're looking at heap manipulating programs. An example is on the right. So this is an example of a program wherein you traverse a list and you allocate a fresh node and insert it into the list whenever, uh, whenever a particular node in the list has a value k1. So notice that heap manipulating programs can update pointers. So that's what is happening over here. You're updating the next pointer. And that's what sort of gives intricacy. That's what makes the problem hard. And we're interested in completely automatic verification. And we'd like to explore classes of programs that admit decidable reasoning without any loop invariance. The next problem that I'll be looking at is memory safety, which is the following problem. So if you have a program, it starts with an allocated set of nodes. So over here, the initial set of allocated nodes is given by this reach specification, reach x next nil, which says the set of allocated nodes in the beginning is those that start at x and can be reached using the next pointer until nil. Okay? And as the execution of this program proceeds, you can dynamically allocate nodes, as in over here, or even free nodes. And the question for memory safety checks if the program is such that there is no execution that accesses memory outside of this allocated set. Now notice that this is sort of slightly different from the popular notion of memory safety, wherein you also deal with the buffer overflows as in C, or you handle arrays. So that's not what we're going to look at. We're just going to look at this problem. And again, as before, we'd like to understand if there are decidable classes of programs that let you do this. So let me sort of talk about this result that we had last year at Popple, wherein we introduced this class of programs called coherent uninterpreted programs, for which verification is decidable. And when I say verification is decidable, I mean verification without any loop invariance. So it's completely automatic. And indeed, this was the first class of programs for which run on domains which are infinite. And the decision procedure is sort of very inexpensive. It is a piece-space decision procedure. So for this paper, the main results are as follows. We considered two problems: assertion checking and memory safety. And for the first problem, we sort of identify that the restriction of coherence that was sufficient for decidability is no longer sufficient here. And that's because of this updatable maps in heap manipulating programs. And so therefore, to sort of alleviate this problem, we identified this class of programs called alias-aware programs. And alias-aware programs in conjunction with coherence gives you decidability. And for the next problem, our results are as follows. We sort of consider, we identify a class of heap structures, or set of heaps for which, we identify a class of heap structures called forest data structures. And these heap structures are such that they give you the aliasing information for free. And for this class of structures, if you look at the memory safety problem for single pass programs, that problem is decidable. So with this, let's look at uninterpreted programs. These are imperative programs wherein that use constants and functions, and that use vocabulary which has constants and functions. But these constants and functions are uninterpreted. And these programs take as input a first order structure, and that first order structure gives you the interpretation of these symbols. So here is an example. So here is the syntax of uninterpreted programs. You have loops, conditionals, composition, and you have assignments, and you have function computations. So the function f there is an uninterpreted function. And assertions and conditionals are Boolean combinations of equality atoms over variables. Let's look at the verification problem for uninterpreted programs. It says that if you have a program P and a post condition phi, then P satisfies the post condition if it is the case that for every input data model M, so recall that the data model gives you the interpretations to the symbols in the program. So for every data model M, and for every execution of the program, such that that execution is feasible on M, is it the case that the assertion phi holds at the end of the execution? So this verification problem sort of asks if some property holds for all data models, and that is sort of very crucial to understand the rest of the talk. So in general, verification of uninterpreted programs is undecidable, and coherence is the restriction that we require for decidability. But it turns out that the restriction of coherence is sort of intricately tied to this notion of terms that I'm going to talk about right now. So on the left, I have an execution of an uninterpreted program. This execution, as it proceeds, computes terms and accumulates some assumptions over these terms. So for example, in the beginning, the variable x, which is the yellow square, points to the ground term x0, and the variable y points to the ground term y0. And as you proceed, you accumulate assumptions. So here you will accumulate the assumption, the term x0 not equal to y0. And as you proceed, you compute newer and newer terms. And then you may accumulate more assumptions. So at the end, x points to the term f of x0. And similarly, y points to f of y0. And you accumulate the assumption f of x0 equals f of y0. So this notion of terms is sort of important. It is nice in the sense that it lets you reason about all first order structures in a symbolic fashion. And it is also sort of very crucial to the notion of coherence. And with that, let's talk about coherence. So coherence is the property of executions. Okay? It says that in an execution, you're not supposed to recompute terms. Or in other words, if you're recomputing a term, then the term that you're recomputing is already present in some variable. And there is another restriction called early assumes, which is sort of technical, and again it talks about terms. And the bottom line is that this notion of coherence is intricately tied towards the notion of terms. And if we want to use the notion of the machinery of coherence for heap manipulating programs, we need to define terms. With that, let's look at uninterpreted heap programs, which is the theme of the talk. So uninterpreted heap programs are regular imperative programs, as before, except for they have commands that let you manipulate the heap. So you have commands that let you derefer locations. So x.d says that you read the value of the pointer d on the location x. And similarly, we can update some pointers. So x.d can be updated to the value of a. And you can also allocate and free nodes. So the main reason to look at heap manipulating programs was the following observation, that one can model pointers as uninterpreted functions. So by that I mean the following. On the execution on the program on the left, if you look at the dereference x.key, it can be thought of as computing a function key of x. Similarly, the dereference x.next can be thought of as the function next of x. Now, with this observation, it's natural to ask if one can directly sort of port the machinery of coherence and get decidability for heap manipulating programs. It turns out that it's not entirely clear. And that's because even defining the notion of terms for such programs is a tricky task. And for that, let's look at this execution on the left. Here you have location variables x and y, and three other variables z1, z2, z3. In the beginning, you derefer x using the next pointer and read it into z1. And then you say that this value z1 is different from this other value z2. And then you update the value of y.next to z2. And at the end, you derefer x.next again, and you read it into Z3. Now, if the locations x and y are different, then the term stored in Z3 would be equal to next of x0. So x0 is the term that is stored in x. And that's because at the update of y.next to Z2, which is the third line, the value of x.next won't change because x and y are different. But when x and y point to the same location, the term stored in Z3 is not next of x0, but indeed the term stored in Z2. And that's because the map update y.next also affects the value of x.next because they are the same locations. And therefore, x.next points to Z2, which is different from Z1, which is different from next of x0. So the bottom line is that for heap manipulating programs, this ideal property about terms being a symbolic representation of all data structures does not hold anymore. And the crux of the problem comes from the lack of aliasing information, and that's the purpose of this slide. So by that I mean the following. If in the same execution, I were to annotate this execution with these extra assumptions, assume x not equal to y, or perhaps assume x equal to y, then you can indeed define terms, and all the relationships between all the variables can be determined accurately. In other words, heaps don't lie when properly aliased. So with this, we should look at the definition of alias awareness. And this is sort of an intuitive definition. It says that if you have an execution, and in that execution, if you're updating a map, then before that map update, let's say you're updating x.h, the aliasing relationship of x is known with all other variables. And when executions are alias aware, then we get the same property back. That is, you can define terms, and terms accurately represent all the heap structures in a symbolic fashion. So with this, when you can define terms, you can define coherence, and that gives you decidability. So when you have alias-aware programs, and you want to check for assertions at the end of the programs, this problem is decidable when you're also looking at the coherence restriction. It is decidable in p-space. So this is the first result of our paper. Indeed, for alias-aware programs, when you don't have coherence, this is an undecidable problem. So with this, let's move to the next part of the talk, which is the following. Most programs will not give you this aliasing information for free. You might have to manually annotate these programs. So it is natural to ask if we can consider some other restriction that gives you this information for free. Indeed, that's the case. If you restrict the class of heaps that we are working on. So this is one such class called forest data structures. So basically, this is the class of heaps, wherein different traversals from a given location, of perhaps from two different locations, give you different locations. Or intuitively, it's a class of collection of trees and lists. So it turns out that for forest data structures, aliasing information comes for free, and therefore you can get completely automatic reasoning for such heap structures. And therefore, in the presence of coherence and alias awareness, and for the class of forest heap structures, verification is completely automatically decidable. With this, let's move on to the next segment, which is memory safety. Here I've defined the problem of memory safety sort of formally. So initially you have, so for an execution, sigma, you can define the set of allocated nodes as follows. In the beginning, you have some set init. And as you proceed and, let's say, allocate a new node, then then you add a fresh node into the set, and when you free a node, you remove it from the set. And the question of memory safety asks if there is an execution of the program which either dereferences a memory or perhaps frees a memory that is not in the allocated set. It turns out that this problem is decidable. It is undecidable in general. It is also undecidable for forest data structures. But when you look at forest data structures in conjunction with the coherence restriction, this is a decidable problem. And we have a tool that implements this decision procedure. Let's quickly look at the experiments. So we looked at about 20 examples. These are roughly programs that work over lists or trees, binary search trees, AVL trees, or we also consider tree rotations. And our tool sort of quickly verifies these programs. We also sort of try to perturb these programs and induce errors, and our tool can also figure out these errors very quickly. So I've talked about alias-aware programs and how this is crucial for even defining terms and also defining this notion of coherence. And in the presence of alias awareness, coherence leads you to decidability. And then I talked about forest data structures and memory safety. So to conclude, I'd like to say that coherence restriction has been has helped us come up with reasonable classes of programs for which verification is decidable. And in this talk, I talked about how you can reason with heaps. So in general, we've also been working on this restriction for a long time now. An upcoming paper in Takas talks about how you can add interpretations to these uninterpreted programs and still retain decidability. And we also have some results on decidable synthesis. So with this, I think I should conclude. I'm on the job market, so please hire me.
Hi, can you give an intuition how you get around invariance? So can you give an intuition on that? And do you need to compute some kind of fixed point when the program has a loop?
So it turns out that if you have this restriction of coherence, then an execution can be recognized by an automaton. And therefore, the set of all executions of a program that are feasible are on some model is really an automaton. And that's how you can sort of get away from looping rates.
Okay, thanks.
Are there some interesting programs that you looked at that are not coherent or not alias or not alias aware? And
Yes.
Do you have some thoughts on
Yes.
maybe extending it?
You mean looking at the experiments, or in general, what are my thoughts on?
Yes. First of all, are there programs
That are not alias aware? Or not? Yes. So that's a good point. So coherence restriction sort of generally says that if you have a single pass program, let's say traversing a list in one fashion, in one pass, that's going to be coherent. But if you were to, for example, sort a list, then you would require multiple passes, and that might not be coherent. That will not be coherent. So that's roughly the intuition of coherence.
Yeah. Thank you for the nice talk. So as you know, one alternative way to reason about heap manipulating programs is by modeling them as arrays, right? So I was just wondering how your decidability results relate to previous results on array manipulating programs, and also what kinds of insights we can get from your results about decidable fragments of the theory of arrays.
So are these results for loop-free programs or they have loops?
They have loops.
Okay, so I'm not sure. So maybe you can talk about them a bit more. As in, what is the notion of why do you get decidability?
I mean, there's several papers, but you know, like, and they have several technical restrictions. I was just like curious if you know about them and whether you've thought about it or not. Okay.
The array property fragment in general has several complex restrictions, and in some sense, this is so. For example, it doesn't reason over numerical domains, which the array property fragment can in fact do it. It can have subproblems that can just be batched off to numerical integer domains, right? So the abstraction here does not in fact do that, and we reason over sort of all models, abstract data domains. But as Umang mentioned in one of the slides, there is extension to doing theories and things like that. So perhaps we can get a little more power by combining both the heap manipulating program work that we have right now and the work that has theories where we do some linear order, commutativity, associativity, things like that. So that's roughly where we're heading with this.
There's one more question.
Thanks. I noticed that your programming language was sequential, and I was wondering if it would make things a lot harder if you had, say, parallel composition thrown in there.
I guess so. So in fact, there is a recent paper in FSTTCS this year that talks about this restriction, but for coherence, for concurrent programs. Indeed, it's likely that computing terms is going to be hard even there. So I don't have a lot of intuition, but that's something that I'd like to add.
I think now let's thank the speaker again.